Good morning, dear students. Let us continue the topic, that is electromagnetic induction. Okay, it's the part 4. Up to the last class, we have studied the induction type. That is, induction can be classified into two types. That is self induction and the mutual induction. Okay, so self induction means what? So, inducing an EMF in a same coil or inducing an EMF in a coil due to the variation of the current in the same coil. Okay. The expression of the induced EMF of solid for the self induction was what? E is equal to minus L d I by dt. Okay. The term L is a constant, that is nothing but coefficient of self inductance or simply self inductance. Okay. Next, let's see when a self induction or self inductor is expression of the self inductor for a solenoid. Okay, that is self inductance of a solenoid. Okay, you can see the diagram here. There are certain ring like structure. Okay, you just imagine the helical spring. During your first PU classes, you have performed the experiment, that is spring constant. You have seen the spring structure, isn't it? So that is helical form. In the helix manner it will be. Okay, so another end is connected to measure the current. Okay, so the term solenoid, okay, consists of a long insulated wire wound in the form of a helix like your spring. Okay, where neighboring turns are closely spaced. Each turn of the wire in a solenoid can be regarded as a circular loop. Okay, when current flows through the solenoid, the net magnetic field is the vector sum of the field due to all the turns. A long solenoid means here the length of the solenoid will be large compared to its radius. So you can see here the length of the solenoid, and if we see the radius value, it will be very small. That is, if it is the initial first phase, okay, the radius value, that is from the center, the value is very small when we compare to its length. Okay, here let's find out the expression of the solenoid. So consider a solenoid of length L and cross sectional area A. So in the diagram you can see the solenoid is there, its length is L and area of that cross section is A. Okay, next, suppose the solenoid has n turns. Okay, when a current I flows in the solenoid, the uniform axial field of magnitude. Okay, actually there is one standard derivation for that. You have to find out the value of the magnetic field in a solenoid, that you will study or already studied in the topic, that is magnetism matter concept, moving charges and magnetism. Okay, B is equal to mu naught small n I. Okay, mu naught n I. Mu naught is the permeability. Okay, here the magnetic field is directly proportional to the current. Okay, so in order to equate, the constant term arises, that is permeability. That is the constant term, that value is 4 pi into 10 raised to minus 7 Henry per meter. Okay, the small n can be written as n upon L, number of turns per unit length. Okay, so in the place of n, here you can see n upon L. Okay, next, so the uniform magnetic field is generated in the core of solenoid. That expression is given by what? B is equal to mu naught Ni divided by L. Okay, the field strength outside the core is very negligible. Okay, the magnetic flux linking the single turn of the solenoid is given by pi is equal to BA. If the initial only one turn, simply BA, that is pi value is equal to BA. Okay, suppose if since in the solenoid the magnetic flux will be linking through the n turns. Okay, so the formula is given by, that is pi equal to n into B into A. Next, what you have to do? In this expression, substitute the value of B. Okay, the expression can be written as mu naught n square A into I divided by L. Okay, small n. Mu naught is permeability, capital N is number of turns, A is area of cross section, I is the current in the solenoid, L is the length of the solenoid. Okay, so we know that the self-inductance is given by the term pi is equal to Li. Okay, you know that in the previous class you have already studied regarding that, isn't it? So L can be written as pi I. Okay, so in this equation substitute the value of pi. So pi is mu naught n square A I divided by L into whole divided by I. So I will get this expression. So the self-inductance of a solenoid is given by the expression mu naught n square A L. So this derivation is not there for you, but you should know the expression. Okay, they will ask the expression for 1 or 2 marks. Okay, mu naught n square A upon L, or simply you can write L is equal to mu naught small n square A L. In order to explain term, what is mu naught here? Mu naught is the permeability of the free space. N is the number of turns per unit length. A is the area of cross section. L is the length of the solenoid. Okay, understood? Okay. Next, let's see some problem. Okay, current in an inductance of 1 millihenry. Okay, inductance value 1 millihenry is reduced from 5 milliampere to 0 in 1 millisecond. Find the induced EMF. Since it is a self inductor, okay, what is the given thing? L is 1 millihenry. Okay, next, Di means final current value minus initial current value. Final current value is 0, initial current value is 5 millihenry. So 0 minus 5 milli, so value is 5 milliampere. Then the time interval is given, variation of the current in the time interval is 1 millisecond. Okay, next, EMF induced in the coil is given by the formula. What is that formula? E is equal to minus L di by dt. Okay, next, what's the value of L here? Simply 1 milli. Instead of that, that is 10 raised to minus 3. What's the di value? Minus 5 into 10 raised to minus 3. Okay, next, minus 3. Okay, value 1 into 10 raised to minus 3, which one? Time. So finally I will get 10 raised to minus 3, these two term cancels. Okay, finally what it remains? Simply 5 into minus minus also plus, it will be 5 into 10 raised to minus 3 volt, or simply it will be 5 millivolt. Okay, next problem. Next, what is the self-inductance of a solenoid of length 0.5 meter, area of cross section is 0.005 square meter, and total number of turns is 1000. Okay, so in a solenoid, okay, solenoid is there here, its length is given by 0.5 meter. Next, area of cross section, that is A value is given by 0. It should be 005. Okay, there is a mistake here. 0. Okay, make the correction while writing the problem. 005. Okay, 0.005 square meter. Next, capital N is given. Total number of turns is 1000. So, in the formula, you can use directly the formula, that is L is equal to mu naught capital N square A, okay, A upon L. Okay, you can directly use this formula. If you use this formula, no need to do this again. You can directly substitute. If you use the formula mu naught and small n square A into L, then rearrange the form, that is n is equal to n by L. N value is 1000, L value is 0.5. So you will get 2000. Okay. Next, so formula, either you can use L is equal to mu naught n square by AL, or you can use this one, mu naught n square capital N A upon L. Mu naught is nothing but, I have already said, permeability constant value, 4 pi into 10 raised to minus 7 Henry per meter. Okay. Next, n value, if it is small n, it is 2000. If it is capital N, substitute the 1000 square of that, okay, into A, 0.005. And finally, L value. If is this formula, substitute in the denominator. If in this formula, substitute, that is 0.5. So finally, what I will get? 0.0025. Okay, 0.0025. Okay, these are few problems on the self inductor and self induction. Okay, that is self inductance of a solenoid. Let's continue the next concept. Before that, one more problem. A long solenoid with 15 turns per centimeter, okay, has a small loop of area 20 centimeters square placed inside, normal to the axis of the solenoid. Okay, if the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced voltage in the loop while current is changing? Okay, so there is a solenoid, number of turns is given, that is n by L, 15 turns per centimeter. If I convert in terms of meter, it will be 15,000. Okay, area is given, area of that solenoid is how much? 20 centimeter, sorry, 2.0 centimeter square, that is 2 into 10 raised to minus 4 meter square. Next, di by dt. Di is nothing but final current minus initial current. Final current is 4, initial current is 2. They have substituted the value, divided by time period is 0.1. How much you will get? Rate of change of current is 20 ampere per second. Okay. Next, induced voltage, nothing but induced EMF. Okay. So, E is equal to d pi by dt. So, pi value is nothing but BA, isn't it? We know that BA value, pi value is nothing but mu naught, B value is mu naught and L by I. Okay, that is magnetic field of the solenoid. B is equal to mu naught small n I. Okay, or if I substitute n is equal to n by L. So isn't it the same formula here? In the place of B, they are substituted. B is equal to capital N by L into I. Okay. Differentiate. Here mu naught is constant. N by L is also constant. Take that outside and finally what you will get? A mu naught N by L into di by dt. Next, one by one substitute the value. A is how much? 2 into 10 raised to minus 4. Mu naught constant value, what is that? 4 pi into 10 raised to minus 7. Okay. Next, N by value is also 15,000. Rate of change of current is 20 ampere per second. If I substitute and finally calculate how much I will get, 7.5 10 raised to minus 6 volt or 7.5 micro volt. Okay. Next, mutual induction, isn't it? So in the diagram you can see two coil, isn't it? In the one P is primary coil, S means secondary coil. B, here the magnetic flux is passing through the primary coil as well as secondary coil. Okay, it linked with both the coils. So mutual induction is the property of two coils by virtue of each opposes any change in the strength of the current flowing through the other by developing an induced EMF. Or it is the phenomenon in which there will be a change in current. One coil causes an induced EMF in the another coil placed near to the first coil. Okay. So here coil in which current changes. Okay, here current is changing. So this is primary coil and inducing EMF is the secondary coil. Okay. So finally, how we can define the term mutual induction? It's the phenomenon of inducing the EMF in a coil due to change of current in a time with the nearby coil. Okay. You can see the circuit diagram over here. There is a coil, primary coil connected to the battery and the tap key, and secondary coil connected to the galvanometer. Okay. Consider a coil connected to the battery through a key. This coil is a primary coil. Another coil is placed near the primary coil connected to the galvanometer, which is called secondary coil. Okay. What happens if I press this key? Okay, circuit is closed. Current through the P start to increase, isn't it? Current through the P increases. So current increases means number of magnetic flux also increases. Okay. That it gets linked with the secondary coil. The magnetic flux linking through the secondary coil changes. Though induced EMF is produced in the coil. So in the secondary coil, EMF will be induced. Voltage variation occurs. EMF induced in the secondary coil due to change of the magnetic flux linked with the coil. So current start to flow in the coil. Okay, if current start to flow, we can see the variation of the current in the galvanometer. Okay, so finally this inducing EMF is called by the term mutual induction. Got the point? If I close the key of the primary coil, current start to increase in the circuit of the primary coil, so magnetic flux increases. So these primary coils magnetic flux linked with the secondary coil. If magnetic flux linking the secondary coil results in the variation of the EMF in the circuit. Okay, there will be a current generation or current start to flow in the circuit of the secondary coil. Okay, so how we will come to know that current is varying or current has been generated in the secondary coil? By deflection of the galvanometer. Okay, next coefficient of a mutual induction, which is similar to a self induction. Okay, coefficient of mutual induction or mutual inductance. Okay, let pi be the magnetic flux linked with the secondary coil when a current I flows through the primary coil. Okay, so here the term pi b is the notation when magnetic flux linked with the secondary coil. Understood? It is given by the constant term pi b is equal to m I. Okay, m is a constant for pair of coils, where m is called as what? Coefficient of mutual induction, or we can use another term, simply mutual inductance. Suppose if current is of unity, then magnetic flux linked with the secondary coil will be equal to the mutual inductance. See here, the mutual inductance of a two coil is numerically equal to the magnetic flux linked with one coil when unit current flowing through the neighboring coil. So magnetic flux linked with one coil means here secondary coil, current variation means here primary coil. So you should remember that current variation will be always in the primary coil and magnetic flux linking will be with the secondary coil. Okay, next, then what happens to the EMF induced in the secondary coil, not in the primary coil? Okay, EMF will be induced in the secondary coil. According to the definition or from the Faraday's law, E is equal to minus d pi by dt. Okay, substitute the value of pi as mi. So I will get the equation E is equal to minus m di by dt. Okay, suppose if I take rate of change of current as 1, then what we can say? Just the magnitude value E is equal to 1, that is rate of change of current minus value. Okay, the mutual inductance of two coil is equal to the EMF induced in the coil. Okay, when the rate of change of current in the another coil is unity. Okay, got the point? When we can say mutual inductance is equal to the induced EMF only if rate of change of current in the primary coil is of unit value. Okay, next, suppose we have already know the value SI unit of self induction. Simply the inductance SI unit always remains constant. Okay, SI unit of inductance is 1 Henry, or simply Henry, HENRY, or you can use the capital term H. Given condition, if E is equal to 1 volt, rate of change of that current is 1 ampere per second. Okay, so in this formula what you can say? If E is equal to 1, then di by dt is equal to 1. Okay, simply I can say I is equal to, that is M is equal to 1. Rate of change of current decreasing, which you know that from the Lenz's law it always opposes the increase in the magnetic flux link in the current start to oppose the further increase of the current in the circuit, isn't it? Okay, rate of change of current will be negative. Okay, so mutual inductance of two coils is said to be 1 Henry. Okay, when we can say it is 1 Henry? If 1 volt EMF is induced in the one coil, means which coil here? Secondary coil. When the current in the other coil, means what here? Primary coil, changes at a rate of 1 ampere per second. Okay, so in case of mutual induction, you should carefully remember the concept that in primary coil, okay, always the current varies. Okay, primary coil. Next, in the secondary coil, induced EMF occurs. Okay, due to variation of the current in the primary coil, EMF will be induced in the secondary coil. That is what the mutual induction concept says. Okay, you should remember that concept very carefully. Okay, next. So the derivation is not there, but just I will give some idea regarding the derivation. Okay, final expression you should know, which is similar to your self inductance of a solenoid. Okay, mutual inductance of a two coaxial solenoid. Okay, so two coaxial means the which has been in the ring manner like this. If one coil is a primary, another coil will be another side, which will be insulated on a single core. Okay, from the same iron core. In the one side primary coil wounding will be there, another on the same side in the opposite direction secondary coil has been winded on that core. Okay, let the length of the coil, here nothing but the length of the sunlight remains constant. Okay, so next in the diagram you can see here, isn't it? P means L and L. P primary current variation in the secondary induced EMF. Okay. Next, first term, the magnetic field due to the primary solenoid. Okay. Field, let the term B1 is equal to mu naught N1 IN. Okay. Simply that is from the term of solenoid, B is equal to mu naught N I. So in the previous derivation, I have used the capital N by L. You can use any one of that, but you should know the relation, that is N is equal to, okay, capital N by L. Small n value is equal to capital N by L. You should remember that concept. Okay. Next, the magnetic field. It is the known expression for us. B is equal to mu naught N. Since there are two coils, B1 is notation used for the primary coil, isn't it? Okay. B1 is equal to mu naught N1 I1. Mu naught permeability of the free space. Okay. Next, if there is no any core. Next, N1 number of turns of the primary coil. Okay, that is N1. I1 means current variation in the primary coil. Okay, current variation in the primary coil. Next, how we can write the magnetic flux linked across one turn of the secondary of the solenoid. Secondary solenoid, pi is equal to B A. Here B value should be, instead of B you should write B1 A. Okay, understood? So the magnetic flux variation of the second coil with respect to first coil for only single one turn. What's that? Pi T1 is per turn, that is simply B1A. So if there are n turns, I can write B is equal to mu naught. Substitute the value of B here, B1 here, that is mu naught N1 I into A. If I substitute the value of N as N by L, what I will get? Mu naught N1 I1 A divided by L. Okay, mu naught permeability, N is the number of turns, I1 is the current in the primary coil, A is the area of cross section. Here the area of cross section of both the coil are same. Okay, number of turns varies, area of cross section is same. Next, here magnetic flux linked across the end turns of the secondary solenoid. Okay, so if it is linked with the secondary solenoid, initially it was the expression for the only one turn. Okay, if there are n turns of the secondary solenoid, so here pi means what? Pi n b a, isn't it? Okay, so you have to write in the place of n, it will be n2, secondary turn flux with respect to first one. So the expression can be written as what? That is mu pi to 1 is equal to what? Simply mu naught n1 n2 I1 A divided by L. Okay. Next, so the magnetic flux relation, the magnetic flux linking through the secondary coil will be equal to the directly proportional to the variation of the current in the primary coil, which is given by the constant term pi to 1 is equal to m to 1 I1. Okay, substitute the value of pi to 1, what I can write the expression. So m to 1 m to 1 will be equal to pi to 1 divided by I1, isn't it? Okay, pi to 1 values mu naught n1 n2 a divided by L. Here I1 that will be in the numerator as well as denominator, that term cancels. Or also you can write mu naught n1 and n2, okay, mu naught n1 n2 a into L. So the area of cross section, area of the circle, simply pi r square, r1 square. Okay, if I substitute the value of a as pi r square, how we can replace the term? Okay, how we can replace the term of m to 1? That is simply mu naught, okay, mu naught small n1 small n2 pi r1 square L I2, okay, or L I1, sorry, it will be L I1. Okay, so this expression I will get, okay, m to 1. Similarly, we can find out the magnetic field value due to the secondary solenoid. Same concept, that is M12. So here, instead of magnetic flux linked with the one turn of the secondary solenoid, it will be applied to the magnetic flux, okay, of the primary solenoid. Okay, vice versa case, the final expression will be, both the term will be same. Okay, the final expression of the both the value will be same. So the mutual inductance of a two coaxial solenoid, that value is given by mu naught n1 n2, n1 n2 small, okay, n1 n2. If I substitute the value a as pi r square, it will be mu naught n1 n2 a L. Substitute the value a as pi r1 square. Okay, you will get the expression. Okay, only you have to remember the final expression, which is that mu naught n1 n2 pi r1 square L. Okay, next, some few important terms. Suppose if two solenoids are wounded on a magnetic core of relative permeability. Okay, if there is no core, there is no any core, simply only mu naught term, free space value. If there is permittivity, means if it has been wounded on a magnetic core of relative permeability, that is, okay, mu r, then the expression can be written as mu naught mu r n1 n2 a upon L. Okay, next, suppose if the solenoids S1 and S2 have number of turns n1 and n2 of different radii r1 and r2, given case is that r1 is less than r2, in that case use this formula. Okay, that is capital M is equal to mu naught mu r n1 n2 pi r1 square divided by L. Okay, so last one point, one more. So your mutual inductance depends also on the relative placement of the solenoid, how the solenoid has been placed. It also depends upon their geometry, their separation, that is, and also the relative orientation. In the next class, let's see some problems on the mutual inductance of a solenoid and simply a mutual inductance concept, okay, and a small concept regarding the generator, its expression, the expression of the EMF induced in a generator, okay. Okay, I'll stop here.